Okay, this lecture is going to be on flat plate drag and some theoretical calculations or results from theoretical calculations. Okay, first thing what I want to discuss, and we've alluded to that a few different times in the lectures, is a boundary layer. So, if we have a free stream velocity coming in, it's going to have the fluid going over a flat plate. This is going to represent our flat plate that's in the free stream. The fluid will have a density and a viscosity. The viscosity, as we went over, you can think of that as sticking to a particular surface. A boundary layer is going to develop. If we represent this, we're going to call this a boundary layer. If you have a flat plate, such as this paper, air or liquid or water going over it, we're going to have what we're going to call and define as a boundary layer. Boundary layer is going to be a layer that is going to be a boundary between where you make the assumption everything out here is going to move with a free stream velocity of nearly the free stream. Everything in here is going to vary from this point up to the top of the boundary layer, and we'll represent this thickness of the boundary layer as delta. The boundary layer thickness, from this point we're going to have what's called a no-slip condition, meaning V equals 0. So right at the point, at the plate, we have no slip, velocity 0. Then from this point to the top of the boundary layer, the velocity is going to vary. Now, depending on different models that you can have a linear variation from V0 to V infinity, parabolic, or other ways to approximate or come up with the exact solution of this boundary layer. But again, the velocity of the fluid in this boundary layer varies from 0 to the top of the boundary layer, where it is going to have essentially the free stream velocity. It's got to vary some way, exponentially, linearly, parabolically, so on and so forth. You can come up with a bunch of different models to scale that. Okay. And going over what we just defined last class, or a few classes ago, this is going to be a representation where you have a streamlined profile as opposed to a bluff body profile. So friction is going to dominate. So we have a solid, we have our fluid, we have our friction, our drag friction is going to be a function of a Reynolds number. So the coefficient of drag and the drag is going to vary as the Reynolds number varies. Okay, Kármán made an analysis of the flat plate and assumed that the velocity was going to be parabolic. Came up with a velocity, or came up with a function that was parabolic in nature, put the boundary conditions, V0 here, V infinity at the top, and came up with a way to model the velocity. From that, he was able to determine a local coefficient of friction. Once you have the function, you can perform calculus or integral methods to come up with all the different variations of velocity that are going to result in shear stresses, which again, that's going to be beyond the scope of this class. Add up all those shear stresses to come up with a coefficient or a total force that's going to be acting on your flat plate. So used integral methods and determined a coefficient of friction, and it was within 10% greater than the exact solution. So this first attempt was able to come up with a fairly accurate way of representing a local coefficient of friction. CF is going to be the local coefficient of friction. So at this point there will be a local coefficient of friction. At this point there will be a local coefficient of friction here, here, and here, which relates to the stress that is seen at this particular point. Remember, stress is going to be the force over the area. So if we don't have things that are going to be the same across this, you have to use integral methods or calculus to come up with what the total force is going to be. So the shear stress here may be different than the shear stress here, and you have to make that assumption that it is going to be. And so therefore you'll have a local coefficient of friction, which relates to this local shear stress. So again, CF is the local coefficient that relates to the local shear stress and not the total force. And again, integration is going to be beyond the scope of this class. Alright, continuing this, Blasius performed an analysis and came up with results for a smooth surface. And a Reynolds number within the range Reynolds number within 5 times 10 to the 5th and greater than 2500. Again, this is where you transition to turbulent flow, laminar flow, and creeping flow. And determine that the local coefficient of friction is 0.664 divided by Reynolds number at a position x to the 1/2. So again, that's the local coefficient of friction. So if you're at this particular point, x would be, if you're 0.2 meters downstream, 0.5 meters, 0.8 meters, wherever you are at a particular point, that is where this is allowed to be a variable. You can find the coefficient of friction at a point on a flat plate along that flat plate. That is again going to be a local coefficient of friction. After coming up with what the coefficient of friction, again using calculus techniques, it was determined that the coefficient of drag equals 2 times the coefficient of friction evaluated over the entire length, which which ends up being 1.328 divided by a Reynolds number raised to the 1/2 power. Where this is again the coefficient of friction evaluated at the length of the plate. And this is going to be your Reynolds number evaluated at the length of the plate. Okay, let's go through a sample calculation. Okay, we're going to calculate the Reynolds number, the coefficient of drag, and the force of drag on a flat plate that is streamlined with the flow. And the size of the plate will be 2 meters by 1 meter. Could be represented a smaller scale, 2 meters this way, 1 meter this way, flow going over the top of it, so the length of the flow is going to be 1 meter to evaluate our Reynolds number. Air is going to be moving over top of it. Let's say it has a velocity of 0.22 meters per second. The density is going to be 1.201 kilograms per meter cubed, and the viscosity is 1.8205 times 10 to the negative fifth pascals times a second. So the very first thing we want to calculate is our Reynolds number to determine if we can use these formulas. Reynolds number needs to be within that range, and again we have to have a flat plate that's smooth. So Reynolds number, rho VL over mu, 1.201, 0.22. The length is going to be 1. Comes up with a Reynolds number of 1.5 times 10 to the fourth. Therefore, the Laminar-Blasius result is going to be applicable for this case. Now to calculate the coefficient of drag over the entire plate is 1.328 Reynolds number based on length raised to the 1/2 power. Taking 1.328, dividing by that number square rooted, and you get a coefficient of drag of 0.011. And finally, to come up with the force of drag is 1/2 the coefficient of drag, rho v squared a. Substituting our numbers in, 1/2 times by 0.011, density is 1.201, the velocity is 0.22 squared. Now we have to come up with our area. And again, what we used for the sphere, we had to use the profile area. Now what we're going to use is the top area, the area that the fluid is coming in contact with. Length times width, which is going to be, in this case, 2 times 1, which is 2. And when you substitute the numbers in and plug it into your calculator, you should get a force of 6.4 times 10 to the negative fourth newtons. Alright, that concludes the lecture on the theoretical calculation of drag over a flat plate.